logistic growth into K. So let's think about this. When you first learned exponential growth, they gave you kinds of problems that were like, hey, you put two little froggies in a frog pond, and they have eggs, and they produce more froggies, and then more froggies, and then more froggies, and it grows exponentially, right? It just keeps whoosh, when all the froggies are multiplying together. Or you could even think of like the rabbits, as it's like rabbits mating, right? Exponential growth. But let's say we have this frog pond, and they keep growing and growing and growing. Is that really feasible that you could have exponential growth in this frog pond? No. How come? What's that, Kim? They'd run out of room. They could die. They could get diseases, overpopulation. So logistic growth takes that kind of those instances in mind. So basically, you start out exactly like you would in exponential growth. So you're growing exponentially. And then at some value, you're going to hit that point of inflection, and it's going to say, I can't quite grow as fast, and I got to slow down. So it looks like this. And then it's going to reach what's known as the carrying capacity. Okay? So there's a certain amount that that pond can hold. So this is what exponential growth could look like. This guy right here, that point of inflection where it's actually growing the fastest. Do you agree with that? Look at the slopes. If you were to draw all those little mini slopes, is that one growing the fastest? Right? So this point right here happens at the value a over 2. And it's always going to be the y value, not the x or the t or whatever's down here. So it would happen here at like y equals a over 2, or y equals a is the carrying capacity. So what about these slopes? The slopes, they start out, what do they approach? As you go to infinity, what would the slope approach? 0. So I could say if this is my dy dx, right? We can just say f prime even. This logistic growth. I can say the limit as x approaches infinity or t approaches infinity of f of x is going to be what? A. But the limit as I go to infinity of f prime of x would be what? 0, because that's talking about the slopes. Okay? Questions so far? Okay. If you'd like to read this, go for it. Kind of what we're going to be talking about and I talked about. This is going to be the model. We're going to see how to get to that. Okay? Yes? All right. So basically, you're going to have that whole formula. And go ahead and get out your homework for today as well. It's got the formulas at the top. Kind of go back and forth on. Okay. So when you have logistic growth, you can see the formula. It's the second one on your homework there. The y equals. And when you have that value k, when it's greater than 0, you're growing, and when it's less than 0, you are exponential to k. A is the carrying capacity, that's what we talked about. It's the maximum size. Okay, so that's what we talked about. And where it's growing the fastest is at half a. And that's also the what in the graph. The what, Sarah? Inflection. Okay. So this basic equation is for logistic growth. You have to have this variable all be the same, right? This has to be a number. This has to be a number. So in this case, a and k are constants. And this has to be a minus sign. And if it's all set up like that, you're going to have logistic growth. Now, we are going to solve the logistic growth equation But the only time I ever expect you to do this, other than that, I want you to have the formula memorized, and you're going to see why. You ready? Yes, Mr. Rose. Yay! All right. So the first thing we have to do when we're solving differential equations is what? All right, dy's and dt's. What has to be with the dy's? Y's, and with the dt's, the. So we got to separate our variables. So let's first separate our variables. You can always think you can bring that guy over, right? So you're going to divide by what? I always like to leave the k over here. It makes life a little bit easier. Okay? So y and a minus y is with the dy, and then what's left over here then? The k dt. You could absolutely divide by the k, but I think it's easier to just leave it on the other side. Okay, now what? Integrals, integrates. That is great. All right. And then it gives you a hint. What's your hint? Partial fractions! Why would your hint need partial fractions? You have down here, you got two factors. Partial fractions. Here we go. Remember, we are going to add like this. We're going to see what those numerators would equal. So we got to pick some variables to go up there. We usually used to pick a when it's linear. Do I want to pick a though? No, because I've got a different a going on. So it's the first one you want to use. B, and then we can pick c if you'd like. Is that okay? All right. Now what? Find B and C. So what's my seventh, Andrew? So y times what? Plus a minus y times equals. Good. And since that would all mean they had a common denominator, I don't care about the denominator, I'm just looking at the numerators. So let's see, what do you want to plug in for y first? Sean? 0. So let's plug in 0 for y, and I'm left with what? A, B equals 1. So what does B equal to? 1 over A. And Sean, what's the other guy I'm going to plug in for y? A. That's nice that they equal the same thing. Right? Yeah? Okay. So this would mean I have the integral of 1 over y. What goes there? 1 over a plus what's over a minus y? 1 over a again. dy equals your integral of k dt. Can I go ahead and pull out my 1 over a? Yeah. And let's go ahead and integrate. Johnny? 1 over y, the antiderivative is what? Good. And the antiderivative of 1 over a minus y is? Very good. And then over here, the antiderivative of k dt. Awesome. Questions so far? range. We got to solve for y. What do you want to do first? Multiply by a. That's a good idea. And let's do that at the same time. Let's put our ln's together and multiply by a. So this would be the ln of what, McKady?
Y over a minus y.
Good. Equals AKT plus C. Still okay? Now what? Just yeah. What does that equal? Let's write a little fun trick in there. To the KT. Keep going, solving for y. So let's see, y is going to equal, you're going to cross multiply. I'm going to go ahead and distribute as I cross multiply. And then bring my y's over to the same side. Kevin, you okay? Right here? That minus is because you had a minus here. So we do the antiderivative. Do you want to see that out? So, got it? Anybody else? So I factored out a y, divided by what was left. Alright, so far we have y equals ACE to the AKT over 1 plus CE to the AKT. Right? What's the limit as we go to infinity here? A. What is A?
Constant.
The carrying capacity, right? Does that make sense? Okay. But does this match the formula that you have on your homework? No, so there's one more step to do to get it to match the formula that you have on your homework. It wants the numerator to be what? A, so what do I have to divide by? C e to the AKT. Josh? What's it going to be? What does that reduce to? What's the numerator?
1.
Well, those would cancel, right?
Yeah.
So what are you left with?
C e to the oh,
That's
A.
A. And then do 1 over that guy, right? So 1 over CE to the AKT.
Oh, you're dividing it top and bottom.
Plus what?
What's the square?
This divided by this? What's this divided by this?
Oh, divided is 1.
Okay. What's 1 over C the same as? C. And if I bring my E up, I have to be what? Negate it. Is that your formula now?
I think I switched. So
1 plus, right? So, you have solved the logistic growth equation in general. Matt, you want to sit up? You never have to do it again as long as you have the formula memorized. If you don't have the formula memorized, you gotta do it every time. Okay? Sound good? Is that a deal?
that's it.
Alright. What's that count? Yeah, and it's good practice to remember all of this stuff. Okay? Alright. We'll start with an easier one. Then we're going to get to some easy ones. Modeling the spread of the flu. Hope it's not the bird flu. The function f of t given describes the number of people who have become ill with the influenza T weeks. That's kind of important to remember. After its initial outbreak in a town of 30,000 inhabitants. How many people became ill with the flu when the epidemic began? That's an algebra 1. Do A and B. That's pretty algebra 1-ish. Where are you going to plug in for T? When it began, it is at 0. Okay. And you can either like put what it would be exactly, or if you want to use your calculator, you can approximate it. I don't care either way. Unless something is telling you to round, even though you're dealing with people, just don't round. Okay? Unless the problem tells you to round. Set to the nearest. Did everybody get that for A? Okay, let's do B. How many people were ill by the end of the 4th week? So now I'm going to put in A. Cool. Okay, so now part C we do not need our calculators for. What is the limiting size of f of t, the population that becomes ill? So is this logistic growth? What's your A here? 30,000, right? What would your K be? How would you find your K? 1 over, your C is 20, right? CE to the negative AKT. So how could you find your K? 1.5 would equal what? K times 30,000. Alright, the math's confusing at that, but just so we can kind of see what's going on, right? So I know my A, so what's the limiting size? 30,000. Or you could look at the limit as t goes to infinity of f of t, and what do you get out? 30,000 over 1 plus 0, which would be 30,000. Okay? Alright. Yes?
What would it ask you? I was going to ask you, okay, like, would it say solve for K or is K something? No.
Yeah, like, is this exponential growth or decay? What's the constant of growth or decay? But I can't imagine you ever being asked a question like that. Okay? Just in case, yeah. They're pretty, this is what we've kind of talked about. Like, I'm going to be showing you some old AP questions. Okay. Alright, looking at these, are these logistic growth or just a differential equation? Same variable, same variable, same variable, number, minus sign, right? So this would be logistic growth. So it says, when are the equation's growing the fastest? What's your A here? Your A is 20, and it's growing the fastest when? A over 2. So at 20 over 2, which is 10. What equals 10? Time or Y? Y. That's really important to know, because on a multiple choice, they could have T equals 10 or Y equals 10 as two different choices. Okay? So you want to know it's when the Y is 10. All right, do the next one. Evan, what'd you get? Okay, that's okay. Yeah, Y equals 5/2 or 2.5. I don't care what you did. Did everybody get that okay?
You can just do that, like, even though it's
You want it to be that. Yeah, I mean, it's really easy to say that's your A. Okay? What's your K here? Josh, what's your K here? 3.
oh,
So it's KY, A minus Y. Or K variable, it could be P for population, A minus P. Okay? Is that alright? So tell me, let's just go ahead, do something different. What would Y equal here if we solved this? Go tell me what Y equals. Just so we can see how we can manipulate that into the specific or general solution. We know our A, it is 5. Do we know our C? No, that's what we would have to go solve for. Times what? D to the negative 15 T. And then if they gave you a point, you could plug it in and solve for C, right? Is that okay? You guys are all dead today. I was the one going up yesterday. I think I do that all mopey. Alright, this one is an old AP question. The number of moves in a national park is modeled by the function m that satisfies the equation given, where t is the time in years and m of 0 is 50. What is the limit as t goes to infinity of m of t? It's this logistic growth. So you have number, variable, number minus variable. Yee, what's wrong there? So it is logistic, but first we need to rearrange some things. I got to get that out of just the variable part. So what can I do? Well, if I multiply, I want to still keep dm dt. I don't want to multiply that by 200, right? So I don't want to multiply both sides. Factor it out. So if I want to factor it out, what would I put here? 200 over 200. So now you can factor out a what? 1 over 200. Okay, so it's this logistic growth. Variable, same variable. Number, number, minus sign. We are good. What's our A? What's our K? Where are we growing the fastest? Which is what? 100. Sorry, what, Sean? And what? Yeah, thank you. Yes, equals 100. And then the question though says, what's the limit as you go to infinity of m of t? 200. It's your A. That's your carrying capacity. Is that okay? Do the next one. Alright, do the next one. We have the years from the thing last year.
What?
You need to get a drink or something? No, no, no. Alright, Johnny. Tell me what you got so far. Yeah. What does that equal? D what? Okay. And C is the number of thousands of coyotes, right? So it'd be 3 over 2 and thousands. 8. Yes? Got blocked on how to spell that. Okay. Alright. Questions about that? Is a dingo a coyote? It's a dog. Isn't a coyote a dog, though?
No, it's like
He's gonna be
it's like a dog. Yeah, but she said it's like a dog.
Oh, no. Yes. They're all dogs. They're all
You're
all
gonna do their
dogs.
math.
Dogs.
Okay.
So we got dogs.
No,
Well, let's see what you guys can do on this last one with your group. Let's see if you guys can get this last one with your group.
Okay.
Are both of these logistic? Andrew,
What?
are both of these logistic?
No. Top one is not.
All right. Thank you. Ready, go. You get 10 minutes. Give me an interpretation. Give an example of what it looks like.
She just talked really loud like this all the time.
Wait. How we doing? You got A done? Yes. Yes. It is. Okay. So your equation? It's been about 6 minutes. How you doing? This could easily have been a free response question on the AP test. 15. But this should be one that you should be able to do in 10 because others would take like 20. Does that make sense? So you average 15. Alright, 3, 0, and C. Okay, now you ready for your joke for today? You're done with notes in calculus. Not. No, I'm just kidding. You really are. Okay. Okay. You really. I'll show you a real joke. Okay. Is there one more time on that? Did everybody get that? So okay. It's all horrible. I should have stopped the recording. and then omega.